So last time we compared the Riemann and the Lebesgue integrals. So for a bounded function on a bounded interval, we saw that if it is Riemann integrable, then it's also Lebesgue integrable, and the two integrals will coincide. And it's not generally true for infinite intervals because there are other kinds of limit processes which are involved. Okay, and we saw an example. So now let's give a couple of examples to show how to prove the integrability, study the integrability of a function with respect to the Lebesgue measure. So let us take the interval 0, 1 and fx equals 1 over root x. So we want to know if f is Lebesgue integrable. Okay, so this is not a bounded function, though the interval is bounded, and therefore what we do is we look at fn of x equals 0 if x belongs to 0, 1 by n, and then 1 over root x if x belongs to 1 by n to 1. Okay, then fn is all non-negative, and therefore fn will increase to f, because you are cutting off from 1 by n and then n is increasing, so more and more of this interval is taken up. The functions are all increasing, and so it's very easy to see that this increases to f. Therefore, by the monotone convergence theorem, you have that integral f dm1 over the interval 0, 1 is nothing but the limit of n tending to infinity integral over 0, 1 of fn dm1. But this fn is 0 on 1 by n, so this is limit n tending to infinity integral over 1 by n to 1 f n dm1. But fn on 1 by n 1, fn is a bounded and continuous function, implies it's Riemann integrable. Therefore, its Lebesgue integral is the same as in the Riemann integral. So 1 by n comma 1 of fn dm1 is nothing but the integral 1 by n to 1 of 1 by root x dx. And this we know, this is what, 2 root x evaluated at 1 by n and 1, so this is equal to 2 into 1 minus 1 by root n, and that converges to 2, and therefore f is Lebesgue integrable on 0, 1 and integral 0, 1 f dm1 is in fact equal to 2 in this case. So this gives you a way. So this idea, we will do one more example. So one should use such techniques. Take away the portions which are singular, and then use the traditional calculus, because the Lebesgue and Riemann integrals are equal for bounded and continuous functions. Continuous functions are integrable, Riemann integrable, and then you use the usual rules of calculus to compute those integrals, pass to the limit, etc. So this is the idea for this. So let f of x equal to sin x by x whole square, x belongs to 0, infinity, and 1 if x belongs to 0, x equal to 0. So f Lebesgue integrable on 0, infinity. This is the question which we want to answer. So integral f is non-negative, therefore Lebesgue integral is definitely well defined. So 0, 1 f 0, infinity, f dm1 is nothing but integral 0 to 1 f dm1 plus integral 1 to infinity f dm1. On 0, 1 f is a bounded continuous function. because sin x by x converges to 1, as x tends to 0. So this, you have continuity and you have a finite interval. So you have a bounded continuous function, implies Riemann integrable, implies Lebesgue integrable. So it is Lebesgue integrable on 0, 1. Now what about 1 infinity? So you now define fn of x is equal to 1 over x square if 1 less than or equal to x less than or equal to n, and 0 if x is bigger than n. So fn is all non-negative, and in fact fn increases to the function 1 over x square on 1 infinity. Therefore, integral 1 by x square, so, or rather g, let me call it, g dm1 on 1 infinity is the limit of n tending to infinity, integral over 1 infinity of fn dm1, and that is nothing but limit n tending to infinity. Now the function is 0 after n, and so this is just the integral from 1 to n g fn dm1, and that is equal to limit n tending to infinity of integral 1 to n, oh, I shouldn't write 1 to n here, let me write 1n dx by x square. Now 1 by x, this is the Riemann integral, and since fn is a continuous function on a bounded interval, it's Riemann integrable, and Lebesgue integral is equal to the Riemann integral, and that's equal to limit n tending to infinity. This is minus 1 by x, so 1 minus 1 by n, which is equal to 1, so which is finite. So g is integrable on 1 infinity. Now fx equals sin x by x square, and therefore mod fx is less than or equal to 1 by x square equal to g of x on 1 infinity. So since g is integrable, this implies that f is integrable on 1 infinity. So f is integrable on 0, 1 and 1 infinity, and therefore f is integrable on 0 infinity. So this is how we compute, we can compute the integrals, or we can study the integrability of functions. Okay.